record. There we go. All right, now we're recording. Time to take the quiz again, gentlemen. All right, first off, the source and drain of a P-channel MOSFET are doped with donor atoms. So we are aware that traditionally an N-type semiconductor is doped with donor, and a P-type semiconductor is doped with acceptor, right?
So that should be false.
That's the trick. It's not. Because when it comes to MOSFETs, the P channels are doped with donor and N channels are doped with acceptor. So this is true. So when it comes to questions like this, there's no equation. This is just general recollection. It's inverted. Donor goes to P and acceptor goes to N now. And there's another question, another couple questions later on that use the same information.
P-type MOSFET, hold on.
Yeah, so that's important to remember that.
Goes to, P-type MOSFET goes to donor?
P channel has donor, N channel has acceptor. So it flips it from what we traditionally would understand. So this is just like a general recollection thing. All right, now here. Question 2, a MOSFET is off when its channel is depleted. Well, when something's depleted, it's lacking. What is depleted? Carriers are depleted here. If carriers are depleted, there's no flow of current. If there's no flow of current, I would define that as off.
Yep.
So in this instance, when a MOSFET is depleted, it is in fact off. On current of a MOSFET linearly increases with gate voltage. No, this is false.
That's exponential. I remember this.
Yeah, so I'm sure there might be an equation or relationship somewhere, but I doubt we'll ever have to calculate it necessarily. But if so, when it comes to this one, when a semiconductor or MOSFET is on, if you use it in a circuit and you increase, like there's a very small operating voltage limit for semiconductors and MOSFETs of this variety when you're using them in like actual application. Because of that exponential increase of that current, if you increase the voltage past like the rating, it's going to bust your thing. It's going to destroy it because the current's going to go up faster than the voltage can. So that's just something to remember. Another thing, like it's just exponential. It's an exponential relationship, not a linear one. Question 4, threshold voltage of an N MOSFET decreases with higher temperature.
Is that true?
I believe that's true. Threshold voltage does in fact have a relationship to temperature, and it's an inverse relationship. Higher the temperature, lower the threshold voltage. And I believe that's the case because when it's an N-type MOSFET, it is doped with acceptors. So here's the big picture explanation. So threshold voltage, there's a question later on that addresses this exact topic that I'm about to talk about. Threshold voltage increases when your doping density increases. Now, threshold voltage of an N-type MOSFET, N-type is doped with acceptor ions or acceptors. Therefore, we have positive ions floating around in there. When you increase the temperature of a semiconductor, you generate free electrons, right? Those free electrons will combine with the acceptors, creating neutral charges, creating a perceived momentary lowering of the doping density. Therefore, if the total doping density of the system goes down, your threshold voltage goes down with it. Therefore, increasing your temperature in an very important, in an N-type MOSFET, because it's doped with acceptors. If this was a P-type, it would go up. But since it's an N-type MOSFET, it decreases with higher temperature. That is correct. True. So that's like the theory reason behind it. Or at least that's like my interpretation of the theory. All right. Question 5. Higher the doping, lower is the threshold.
Threshold goes.
Yeah. Threshold voltage goes.
Threshold voltage directly correlates to
doping density at the lowest level. Doping density is one of the. There's 3 factors. There's a lot of questions about threshold voltage. It's obviously a big topic. But one of the major factors that produces the threshold voltage, there's an equation for it. We know the equation. We can look at that later if we really need to for the equation sheet. But threshold voltage, one of the major factors is the doping density, and anything that can affect doping density, like temperature, must be considered. but you need to consider the overall higher level interactions based off of the material we're using here. So since this is an N-type that's doped with acceptor, it's going to go down. If it were a P-type doped with donor, it would go up instead. Right down here, question 5 is talking about the similar stuff. Higher the doping, lower is the threshold voltage. This is false, because higher the doping, higher the threshold voltage, because there's more dopants here. It's not specifying an N or P type. It's not specifying an external condition. It's just talking doping density. And we know doping density is directly correlated. So it is false. Almost picked true. False here. All right, question 6. The source of inversion carriers in a MOS capacitor is dopant atoms. This is false. The source of inversion carriers in a MOS capacitor is the thermally generated ones, if I'm not mistaken. But I know for a fact this is false. Later on, there's a question about thermal generation, and I'm pretty sure that's where the inversion carriers come from. At flat band condition, charge density is 0. At flat band condition, there is no external charge across the gate, right? It's just like it's sitting there on a table. If it's sitting there on a table, the charge density on the gates is 0. Therefore, at flat band condition, the charge density is 0. Correct. Most of the applied voltage on the gate drops in the oxide layer. Yes, oxide sucks. That's how I just remember it. I remember it. So when you think voltage drop, or when I consider the concept of a voltage drop, I always correlate it with the concept of a resistor. A resistor causes a potential drop across it. An oxide layer has a higher resistance than a semiconductor or some other metal, right? Therefore, the highest resistance component of the structure that we're working with here, the MOS, the metal oxide semiconductor, right? Is it semiconductor? Is that what the S stands for? I don't want to remember that. I'll go with it.
I think that's it.
Yeah, I think that's it as well. So semiconductor has a relatively low resistance during operation. The metal always has a relatively low resistance. The oxide obviously has the highest resistance of the three. Thereby, it has the highest voltage drop across it. So most of the applied voltage is going to drop across your oxide layer. That's just the theory behind it, and just something you can just remember because it's always going to be true. Question 9. A MOSFET is on when its channel is accumulated with majority carriers. I think this is true. Let me try and compute why real quick. There's a couple questions later on that are referencing accumulation conditions, including one that's talking about the off and on conditions. Oh, there's literally an accumulation question next. So I'll be able to address this one again when we go a little bit later on. But for now, I'm pretty sure the MOSFET is in fact on when it's accumulated with majority carriers. True. In accumulation, here, let's actually, since it's one that's potentially in contention, I'm going to keep a running list of the ones that are like iffy for us. Because remember, even my best one, I only got a 92. I'm not perfect. Question 10. In accumulation, majority carriers pile up at the Si oxide interface of the MOS capacitor. I'm pretty sure this is true. It's something from one of these presentations, the characteristics, I believe. I'm pretty sure that's just true. It's just a recognition fact. All right. For which of the following conditions, it should say does an N-channel MOSFET behave like a gate-controlled current source? So for this one, I made a little like memory thing, or not really memory thing. So when it's a gate-controlled current source, both parameters should be facing the left. So they should both be greater than. So in this case, our answer would be the last one. VGS is greater than VT, and VDS is greater than VGS minus VT. So this is just because, what is it? For which of the following conditions? When your gate voltage is greater than your threshold voltage, and when your, what's the DS? I don't remember what DS is. It might be in the list of symbols. Drain to source voltage. Yeah, okay. Drain to source voltage is less than the gate minus threshold. So this one's like this. This one is more of something that I was just able to just get. I don't have a super good explanation of this. Does anyone else have one? Because if not, we'll pull one later from one of the other PowerPoints. Does anyone know why this is how it is? If not, we'll pull the answer from one of these later, and I'll keep the running tab. We'll add 11 to the list of ones that may be. Well, I know this one's right, but we'll just keep it for later. Question 12. If 5 volts is applied to the gate of an ideal MOS capacitor whose substrate doping is, Na times 10 to the 17th, what will be the voltage drop in the oxide? So you could do the math here, and it's not that hard, because if we look at his homework solutions, we can pull the equation for voltage drop in oxide. It's right here. And we just use a bunch of parameters. Yeah, we would just do something similar to this. We need WD, and then we would need this equation. The only thing, yeah, we just solve for that.
This one here.
So oh, you can draw. That's awesome. So that
Yeah,
one
annotate.
and the one above it. You also need the one above it because you see WD appears. So you also need to solve for WD.
Mm-hmm.
Yeah. So those are the equations here. But it's possible. This is how I'm able to do. It's possible that you can just guess the right answer based. Okay. Are you able to erase those?
Yeah.
All right. So here's how this works. So first off, we know from earlier that most of the applied voltage drops across the oxide. So first off, we can immediately eliminate 2 of these options. 1 volt isn't even half of the applied voltage out of the picture. Now we're dealing with 2 different answers, more than or less than 4 volts. Now, this one, I know that it's more than, just because slightly less than 4 volts, it could be 3.9, it could be that, and then it's still a little bit too small for my taste, because I've done a couple of these problems before, so I know the range. But as I just showed, to solve this proper, if you came in with no information, you didn't know any tricks, you would simply just use these 2 equations. You'd solve for WD, and then you'd solve for V oxide, given your parameters. T oxide would be the only information we were given here is the doping density, so everything else is obviously just going to be given as a constant on the test somewhere, or written on our formula sheets. So that's just how that would be. You would just calculate it that way. But for this example, I'm sure that both of you or everyone's completed homework 6 and understands the use of these equations, or at least just the fact that this is all you need to calculate the drop in oxide. So I know for a fact the answer is slightly more than, just from inspection, because I've done a couple of these before. But the process behind solving it proper is simply using these 2 equations.
Mm-hmm.
All right. And then threshold voltage of a MOSFET depends upon the following. So this is one of those questions I said is going to come up earlier. So threshold voltage, this is the type of question you can look at the equation to find the answer to. But let's think. Substrate doping. Let's just look at the equation then for VT. Where are you hiding? So VT is equal to VFB plus VOX plus this. So we can look across VOX and this equation. Substrate doping is Na. Okay, that appears in here. Na also appears in VOX. So far, we can confirm that substrate doping does in fact matter. Now we look at the oxide dielectric constant. Where does that show up? Oh, cool. It shows up in V oxide. Okay, well now that means VT does depend upon that parameter as well. So now we can add that. Oxide thickness, what is that? Tox, that appears. Oh, what do you know? It's all the above. So that's just an equation inspection. He's had a couple of those before. And you don't even need to, if you just remember and understand what these things are, you can probably immediately understand that everything matters here. But when in doubt, you can always look back at your equation sheet. Question 14. If ES is the maximum electric field magnitude in the silicon, and EOX is the maximum electric field magnitude in the silicon dioxide, which of the following is true for the depletion condition in an ideal MOS capacitor? So this one is just a memorization thing because it's just the depletion condition. It's just a parameter that you can memorize, and that parameter happens to be this one. It's equal to 3 times the silicon magnitude for the oxide. And that's from one of his older PowerPoints. It'd take a bit for me to find it real quick. So we'll write that down just in case if anyone wants to go back to it to talk. But in this case, it's just a list of things. In fact, if I'm not mistaken, you could write this type of information on your formula sheet if you wanted to. You could write this and then its corresponding condition. In this case, it'd be depletion. Which of the following represents depletion condition in an ideal MOS capacitor with P-type substrate? Ideal MOS capacitor is depletion condition. So if I remember correctly, inversion is when it's this condition. So we're not at inversion, we're at depletion. So it should be this one. It shouldn't be equal to 0 here, and it shouldn't be less than 0. This is the surface potential, yeah. So the surface potential should be equal to the Fermi potential in a depletion condition. That's a memorization thing, but I'm sure you could probably do it formulaically. I'm sure it appears in one of his PowerPoints at some point. We'll look back at it, but if it's wrong, but I'm sure 15 is right, but I will still put 15 down just in case.
Oh, that's the shit I ordered.
Listen,
Question
It's just some pictures.
16. How does the threshold voltage of an N-channel MOSFET depend on doping density?
you-
So we're talking N-channel MOSFETs here.
Me. What was happening there?
Is
I just
that,
got the clue.
Hmm?
The context of
would that be the second one?
Second one, you said higher the doping, more is VT. So yes, it should be that one. It should be higher doping equals more threshold voltage. So regardless, I'm pretty sure regardless of the channel type, I think P and N channel type, if you increase the doping density, there should still be that relationship to VT is constant across both channel types. So it should
Okay.
always be higher the doping, more threshold voltage. We talked about that earlier, which is probably just higher the doping, more the VT threshold voltage. Question 17. When voltage drop is 0 in the oxide of a MOS capacitor, what is the bias condition? The voltage drop in the oxide is 0. There is 0 voltage drop across the highest resistance component of the system. What can that tell you about the system? Tells you there's no voltage across the system. What does it mean when there's no
Flat
voltage across the
band.
system? We're talking fault band here, but flat band in reality. Yeah. So question 18, what is the charge density on the gate of a MOS capacitor when voltage drop in the oxide is 0.1 volts? Oh, and oxide thickness, it gives you the constants here. So it gives you EOX and it gives you the oxide thickness. So this is one you can do by calculation. So charge density, you would go backwards. So it gave us threshold voltage, or no, it gave me VOX. All right, it gave voltage drop in oxide. It gave this, it gave this. Well, yes, it did. Or did it give it? Yeah, it gave that there. All right, so it gave us all these different aspects and information, and then it's asking for charge density. So there's an equation later on where we do charge density. Where is it hiding? Yeah, it's right here. Charge on the gate is Q times your doping density times your WD. The reason that WD is important is because since he gave us VOX, we can go back to the VOX equation, which is right here. And we see that WD is a component of the VOX equation. So we need this in order to solve back for WD. We would rearrange the equation to solve for WD, take WD and then put it into our charge equation, solve across. Solve across, and then you're game on essentially, and then it'll give you a value. I've done this question before, which is because the reason I'm moving a little bit faster is since we're taking the test live, I have to make sure we don't run out of time before the test is over. So I'm going a little faster than normal because once we're finished, it will let us inspect the answers, inspect our performance once. So I know from my past attempt that this is 3.5. But I just did a quick explanation of how you use VOX and back use it to calculate WD and then take WD into the charge equation. So we can address that again once it's formula sheet time. Which of the following is true regarding the doping type in the, which of the following is true regarding the doping type in the channel region of the MOSFET? All right, so this is what I talked about earlier, where you need to remember that they're inverted. So N-channel MOSFET is doped with acceptor. Yeah, and then P-type or P-channel MOSFET is doped with donor. So in this case, the answer is B, yes. All right, that's just a fact question recognition. Question 20, what is the voltage drop in a silicon substrate of an ideal MOS capacitor, which is at the onset of inversion? So when it comes to onset of inversion questions, That's one of the things we did on the homework. So there's a formula. Formula's here. So the onset of inversion is what manipulates what. Yeah, this is it. So essentially this whole question is this is part of question 1. So in question 1, we do something that's essentially the same thing. At the onset of inversion, the main parameter that's modified in the onset of inversion is the fact that your depletion width changes. Now, when your depletion width changes, you have to carry that through, and it's asking for the voltage drop in the silicon substrate. Yes. So silicon substrate, that's VG, right? That's what that's called? No, where is it? Yeah, it's this one. Oh, is this surface potential? Yeah, it looks like it. Okay, cool. All right, so this is the formula for that. So the first part when it comes to onset of inversion is you have to recalculate your depletion width, which will be given, or you'll just figure out how to do it. And that's the formula to recalculate your depletion width right there. You take this value of your depletion width that you calculate using the only values it gives you for this is your doping density. And I know, because I did the calculation last time, that the answer is 0.84 volts here. But the process to do it is at the onset of inversion, you recalculate your depletion width, you carry that depletion width down, and you do the voltage drop in the silicon using this setup right here, this system right here. In fact, if you look, it's the exact same answer, 0.84 volts, because it's the exact same doping density. What does that tell you? That means that the method for solving this type of question is literally the same every single time. Assuming given the same density, it's going to be the same every single time. So that's just so when it comes, if you want to see a really good example and understand it fully, you can go to his homework solutions and look to, past the inversion part, because that's essentially what he asked in that question. Question 21, which of the following conditions in an N-channel MOSFET behaves like a gate-controlled resistor? I believe it was greater than less than. I think it was this one. So the only thing that changed was the secondary parameter at where the drain source voltage is less.
No, we start at 8. It goes to 9.
Wow.
Yes.
So I'm going to list down 21 as one that we need to look through the PowerPoint for more explanation, because I myself don't have the proper explanation for it. I just have the guess and check feeling for that one. So we'll go back to that once we submit this. Question 22. If an ideal N-channel MOSFET is biased in the off condition, what is the corresponding surface potential value? So it's biased in the off condition. That means it can have any of these values. So it's an all options is correct system here. It's just one of those things. You got to look at one of these PowerPoints or one of the PowerPoints in the past, and it's just a fact thing. There's no calculation needed here. It's just one of the intrinsic properties of this particular condition. Question 23. I said this earlier. What is the source of the inversion carriers in MOS structure? It's thermal generation. Inversion carriers, this is a fact to recall. Inversion carriers are directly thermal generated. That's all you need to know for that. Which of the following conditions of a MOSFET channel, I feel like that's wrong grammar. Which of the following conditions of MOSFET channels describe correctly the on and off state? I don't know what that is phrased weird. So based off of questions we've answered previous, we can make a guess here that's pretty educated. So when we're talking in the off, let's scroll back up to the one that we answered. We answered 2 questions very similar to this. I believe they were true and false right here. A MOSFET is on when its channel is accumulated. We said it's true. And then earlier, there's a MOSFET off question. Right. And then we say a MOSFET is off when its channel is depleted. Therefore, our answer here should be on accumulated, off depleted, if we're going to be consistent with what we said previously. Boop, boop, boop. Let's see. We'll find out soon. I'll list this one down, but I'm pretty sure it's correct. But so we said on accumulated. Huh. It's got to be that one then. this is the right answer then. Therefore, and this is why you have to be able to look back at your own questions, which is why I'm happy he gave us that ability for our newer tests. Because now, this is still correct. But this is false. Boop. And we'll look back. I made sure to list, we'll look back at 24 from the PowerPoints. Question 25. When the N-channel MOSFET is at accumulation condition, which of the following statements is true? MOSFET is off, VG is less than 0, holes pile up in the oxide. So holes pile up in the oxide interface. This is a question from previously and we answered true. VG is less than 0 in the off state, so that's the gate voltage. And when it's accumulating, this might modify an answer previous. So this should be all options are correct. Because when the gate voltage is less than 0, that means it's a negative voltage value. That means that the MOSFET is preventing current flow. If it's preventing current flow, that means holes are piling up and they're not allowing current to flow. So it's piling up as it states. Therefore, those two conditions can tell you that it is in fact in the off state. Therefore, all the options for question 25 are correct. But if the MOSFET is in the off state at accumulation condition, if it's in the off state at accumulation condition, then we have to consider something previously. No, I'm just going to leave it as it is then. I'm not going to go back and manipulate any other questions. We can discuss it after it's submitted since we have a time sensitive thing here. Question 26. How does temperature affect the threshold voltage? So this type of question has been asked like 4 times. The temperature effects of threshold voltage or effects of threshold voltage, all these things. So it looks like for this test, threshold voltage is probably going to be a hammered down topic. It's going to appear many, many times. So let's make sure we are masters of threshold voltage. So how does temperature affect the threshold voltage of a MOSFET device? So here, notice he doesn't specify a channel type. So with the increase in temperature, the magnitude of threshold voltage decreases. With an increase in temperature, the magnitude of threshold voltage increases. The magnitude of threshold voltage increases or decreases depending on the type of MOSFET, or the magnitude of threshold voltage is independent of temperature. We know it's not independent of temperature. We know that an increase of temperature does not cause an increase in the magnitude of it. So if I remember correctly, based off of the stuff we've answered previously, we should say D, but I'm pretty sure that the answer here is B, and it just decreases. So I think it's a difference in magnitude of decrease across the types, unless we start getting to extreme temperatures. Question 27. If the surface potential is 0.5 volts of an N-channel MOSFET, what is the gate voltage? All right, so surface potential is 0.5. So we can look here at his formula for surface potential. Well, this is a surface potential on set of inversion, but that's not exactly what we want. Guess that's what we're gonna get. All right. 0.5 volts. So, oh, and the doping density is identical to the doping density from the homework. 0.5 volts. N-channel MOSFET. All right, so we have to figure out what the gate voltage is here. So we have to make an educated guess since it's not actually a specific thing. So a surface potential of 0.5 volts is not in the flat pan condition. Therefore, we can eliminate VG is equal to 0. The gate voltage is not 0 here. The gate voltage, a surface potential of 0.5 also does not put us, I believe it does not put us into the VG less than 0 range. So if I were to take a guess here, I'm fairly confident that it is between 0 and the threshold voltage. It is not greater than the threshold voltage here. It's not less than 0. It's not in the accumulation condition, and it's not in the flat band condition. So it should be in this condition. So I'm going to list 27 as one we need to go back to the PowerPoint and take a bigger peek at. Question 28, what is the direction of current flow? So this one is a memorization thing. You just got to be able to recall the answer. And for me, the way I understand to recall this answer is it's into N. That's it. So it's into NMOS and out for PMOS. So in N, out P. So into the drain for N, out of the drain for P. So I just remember in N and then in your mind associate the opposite with P. Because in this question, you could potentially pick in for N and be still wrong because it's not also in for P because they are flipped because of the charges on there. Yeah, see, we got a time charge there. All right. Which of the following is a correct statement on the pinch-off condition? So this is just another memorization thing from the properties. So this is dependent on the electron velocity for pinch-off condition in an N channel. So it just has to do with the velocity. And it's a higher velocity compared with the rest of the channel. Then question 30. When minority carriers pile up at the Si oxide silicon interface of a MOS capacitor, what is the bias condition? Well, the word pile up is a synonym with accumulation. There you go. All right. So, and that's just what that is. That's just what it's asking. And there's a previous question on accumulation where one of the conditions for the all options is correct is this exact question. So he likes to duplicate the questions. But something to note is when he has so many of these duplicate questions, it means if he had like, let's say the threshold voltage where he's had like 5 of them, probably 2 or 3 will show up on the test and you'll have 2 new questions, probably that are result like directly, if I had to take a wild guess, his 2 new questions are going to be like something like these, like charge on gates, that kind of stuff. And then in like the second part, he'll make us do this stuff. Like a couple questions for the multiple choice across a couple of them maybe. But now, so right now I listed 7 questions to look back at if we had time, and we do still have a little bit of time. So we still have 28 minutes, so we can look through all these and confirm. So first off, question 1. Source and drain region of a P-channel MOSFET is doped with donor atoms. This is just a recognition thing. Yes, that is true. Unlike the previous silicons we've been working with, a P channel, which would normally denote acceptor, now denotes donor, and for N, the opposite is true as well. N now denotes acceptor instead of donor. So this is true. P is related to donor now. Q. Yeah, Q2. A MOSFET is off when its channel is depleted. So I said true here. I'm pretty sure that's correct. So the on current of a MOSFET linearly increases with gate voltage. As we said previously, that's an exponential relationship. That's just something to remember. And because of that, it's false. Threshold voltage of an N MOSFET decreases with higher temperature. This is true because an N MOSFET is doped with acceptor type. Acceptor type is a positive. Charge, it has positive ions. Because it has positive ions, aka holes, when you heat it up and free electrons from the intrinsic silicon that still remains, it causes the positive and negative things to recombine, causing a net momentary decrease in the amount of carriers in the system, which cause the total amount of carriers to go down, which causes the threshold voltage to go down because carrier amount. Higher the carriers, higher the threshold voltage, lower the carriers, lower the threshold voltage. Higher the doping, lower the threshold voltage. That is false because that's exactly the thing I just said. Higher the higher, lower the lower. So this is false. The source of inversion carriers is dopant. No, this is the source of inversion carriers. It's later on in another question. It is thermally generated carriers. At flat band condition, the charge density is 0. That is true. At flat band condition, there is no charge potential across the gates. Most of the applied voltage on the gate drops in the oxide layer. This is true. It's just something to know. Question 9. A MOSFET is on. So this is one of the things that might be in contention. MOSFET is on when its channel is accumulated with majority carriers. So we now say false on this. Initially, we said true. We'll find out if this is correct here, but we're going to stick with false simply because that tracks with one of our answers later on. In accumulation, majority carriers pile up at the silicon oxide interface of a MOS capacitor. This is true. Then we have all these. That's one of those. We'll have to go back and talk more about those. Question 12, if 5 volts is applied. Yeah, this is just this is a calculation one that's done almost identically to this portion. You solve for WD using this exact equation, then you solve for Vox using this exact equation, and you will get slightly more than 4. Threshold voltage of a MOSFET depends on the following. You can go look at the equation for threshold voltage. You can see oxide thickness is a factor, oxide dielectric constant is a factor, and substrate doping is a factor. Therefore, all options are correct. Question 14, if the if ES is the maximum electric field in the silicon and EOX is the electric field magnitude in the silicon dioxide, which of the following is true for the depletion condition? So this is one of those things, it's another memorization thing from one of his previous slides. It's just approximately 3 times. And then this is another thing that's going to be a memorization of conditions, and it's just equal to the Fermi potential. This is, I believe this is the onset of inversion condition, and these are probably one of the other conditions, like depletion or flat band or something. But this is the depletion condition for a P substrate system, and this is probably, I think this is the depletion condition. Yeah, this is the condition for flat band if I had to take a guess. How does the threshold voltage of an N-channel MOSFET depend on doping density? Yeah, we've been talking about threshold voltage a lot. When voltage drop is 0 in the oxide of a MOS capacitor, what is the bias condition? When it's 0, it's flat. What is the charge density? This is another calculation thing where you have to go backwards with some of the equations, and we'll go through those when we make the equation sheet in a bit. Which of the following is true regarding the doping density in the channel region of a MOSFET? N channel, as we said previous, is acceptor now, and P channel is donor. Voltage drop at the onset of inversion is another one. This is the actually this question is exactly the same as the homework question, and I exactly get the exact same answer as it's 0.84 volts. And then this is another thing. So I'm not sure if this one is exactly correct, but I'm pretty sure it's the only thing that flips from a current controlled system is that the drain source is now less than as opposed to greater than. If an ideal N-channel MOSFET is biased in the off condition, what is the corresponding surface potential? In here, it's all options are correct. What is the source of inversion carriers? As we said previous, or I said previous, it's thermal generation for inversion carriers. And then here's one that this question is what causes me to second guess a lot, because if I answer, because there are previous questions that are relating to the on and off conditions respectively. So based off of the available answers here, this actually kind of helps you with those questions in the past. So look out for questions like these on the test. So here we said that on is when the channel is inverted and off is when the channel is depleted. We're going to go with it and hope is correct. There's probably an explanation for that in probably this one, if I had to take a guess. When the N-channel MOSFET is at accumulation condition, which of the following statements is true? All the options are correct here. The MOSFET is off in accumulation. VG is less than, therefore, it's a negative voltage applied across the gate, so it's accumulating and preventing current flow. And as it says here, accumulating, holes are piling up at a location, hence the name, accumulation. So this is all options are correct. So if accumulation condition is off, you see, that's why these questions, like, they sketch me out, see? Because look, in the off channel is accumulated, right? Therefore, if you know that accumulation condition is off, then this would be correct. But we'll leave it as is, because I think depletion. No, because the reason you can know that that's that the one I was about to change it to is wrong is because the MOSFET is not on at flat band. It's just sitting around doing nothing. So that's why that's going to be incorrect. All right, we'll finish this up then and submit it and see how we did. As long as we got an 80 or above, I'll be satisfied, and then we can start making the formula sheet and ask for some questions, if any, which there probably are because I'm rambling. Question 27. If the surface potential is 0.5 volts, what is the value of gate voltage? So it varies between 0 and the threshold voltage here. It's not less than, because if it was less than 0, it would be in accumulation condition. And if it's equal to 0, it would be in flat band condition. There wouldn't be a surface potential. And then if it was greater than 0, the surface potential would be a little bit higher than that. And you can solve this numerically by back solving with some of the formulas that we're going to write down soon. What is that? Oh. What is the direction of current flow? This is a memorization thing. It's into the drain for N and out of the drain for P. And question 29, which of the following is a correct statement for the pinch-off condition? and it's directly related to the electron velocity, which is higher than in the pinch-off region than in the general area. And then the last one is when minority carriers pile up, what is the bias condition? Well, pile up is a synonym for accumulation. That's that. All right, let's hope for an 80. Well, we got a 96. That's better than I did. All right, let's see what was wrong, and let's see what was right, shall we? So now that there's no time thing, I'll open it up much easier for people to ask questions, and we can try and explain things that people have questions on, if anything. So let's start off with question 1. Does anyone have any problems with this? All right, cool. Does anyone have any problems with this? Now that we know this is correct, everyone remember off condition. I think there's several states where, I think there's several conditions for off now that I think about it, which is why I'm kind of being a little sussed out earlier. Let's continue through. So a MOSFET is off when the channel is depleted. Cool. On current, yeah, we know about the exponential relationship. Threshold voltage of an N-type decreases. So I had a decent explanation for it previous. If anyone wants me to do it again, I will. Doesn't look like anyone needs a new one. Obviously, this is recorded, so you have all the time. I'll try and get this uploaded to YouTube. It depends on how long YouTube decides to, look over my video, but it should be uploaded by midnight tonight, so everyone can look over it before the exam tomorrow. We did that one. Higher the doping, lower the threshold voltage. We talked about that as well. It's false here. Source of inversion carriers in a MOS capacitor is dopant atoms. We know that this is false, because it's actually thermally generated carriers, not dopant atoms. At flat band condition, charge density is 0. If it's at flat band condition, nothing's happening. It might as well sit on a table. Might as well just be a rock. Question 8, most of the applied voltage on the gate drops in the oxide layer. Oxide layer is going to have the highest resistance, therefore it's going to have the highest voltage drop. At least that's how I think about it in my head. It's probably not the exact reasoning behind why that's the way it is. It might be, but all you need to do is get the right answer here. When it comes to understanding, that's for the master's degree. Question 9, a MOSFET is on when its channel is accumulated with majority carriers. False. We know accumulation condition prevents current flow, therefore it's not on. So because this question is true and the question earlier about depletion is true, that means that there's 2 separate conditions at least that can produce a MOSFET in the off state. Question 10, in accumulation, majority carriers pile up at the silicon oxide interface of a MOS capacitor. True. When you see the word pile up means accumulation. This is just the fancier, cooler way of saying it. All right, and then this is just one of those memorization things that you'll have to be able to do from one of the PowerPoints previously. It's just a relation for gate-controlled current source, and that's probably going to come from one of these PowerPoints because it's a property kind of thing. So in this case, when it's a gate-controlled current source, it's just going to be greater than for both parameters. If 5 volts is applied to on the gate of an ideal MOS capacitor whose substrate doping is this, what is the voltage? So I talked about this twice by now, so it's just some formulas here, 2 formulas, and you back solve them, and then you can find the voltage drop in the oxide. But right off the bat, you can eliminate 2 answers here to make it easier. So right off the bat, you can eliminate 2 answers simply because we know that the voltage drop in the oxide is where the majority of the voltage or the potential across the system drops because it's the highest resistance or whatever. Because of that, you can immediately eliminate slightly less than and slightly more than 1 volt, and you can only choose between these 2. And then at that point, you can either numerically confirm it, or, good rule of thumb is to pick the more than instead of the less than. Good rule of thumb across these types of problems. Question 13, threshold voltage of a MOSFET depends upon which of the following? This is just look at the equation for threshold voltage. It's all of them. Then this is another one of those things where you just look at the PowerPoint and remember it. So for this condition, which is the depletion condition, it's 3 times. Then you look at this. So the condition here is depletion. Depletion condition is another one of those things where you just got to look at it and be able to remember, and it's just this. It's just going to be equal exactly to the Fermi potential. I think this is inversion. This is flat band. And this might be accumulation. I'm not sure. Maybe. Probably. How does the threshold voltage of an N-channel MOSFET depend on doping density? Higher the doping density, more the, yeah. So it's just a direct relationship. When the voltage drop is 0 in the oxide of a MOS capacitor, what is the bias condition? It's flat band or fault band, however you prefer to say it. Fault. Question 18, what is the charge density on the gate? So we haven't had any questions so far, so I'm gonna scroll down to the one question we got wrong. Of course, it's the last question. When minority carriers pile up, so here, so this is why I got it wrong, because I said pile up, and yep, that's a problem. When minority carriers pile up, I think it's the reason, I think it's minority carrier. Let me look at something. I think I figured out what happened there. Where was the last time it said pile up? In accumulation, there it is. So I looked at this question, and since I knew this was right, I went to 30 and got it wrong. Why? Because I missed one crucial detail. In accumulation, majority carriers pile up at the silicon oxide interface. This one asked about the minority carriers, and that's why we didn't get an 100 people. Remember to read the question, because I always don't. I sometimes don't. When minority carriers pile up at the oxide silicon interface, remember that the bias condition is inversion. Those are the conditions for inversion, not accumulation, because inversion is directly related to the minority carriers, hence the name inversion. It inverts which carrier is more important at the moment. Inversion. Or minority carriers. All right, so that's that. So shooting for an 80, we got a 96. That's cool. Took us 40 minutes, which is 4 times my last time, but that's because I sit there and talk forever. So let's start making a formula sheet, people, which will come from here primarily. No one. Let's think. So has anyone started on a formula sheet yet, or have any ideas for them? Because even though I host these things, I'm not a master of this topic by any means. All right. So we'll try our best to find which formulas are best for us. I'll try and, upon the completion of my formula sheet, I'll send a screenshot of it to the GroupMe and politely ask everyone if there's any formulas I missed, please tell me so we can add them. So I'm going to scroll through, I have every PowerPoint open, and I'm going to scroll through every single PowerPoint and look for important stuff. So when I was doing the homework, I spent a lot of time on this slide and this slide and this slide, this slide, a lot of slides here, but this one, I know for a fact that this formula is important. This one right here.
Mm-hmm.
So I'm going to say formula sheet. All right.
Are you going to bed after that?
Yeah.
All right, so let's start. So first things first, this formula right here, I know we use a lot. So this is just your surface potential formula. So get that one down. And remember, ESI is equal to what? Is equal to 3, I think it's equal to 3.9 times no. ESI is equal to 11.7 times epsilon 0, right? If I remember correctly. Obviously, since it's a constant, it's either going to be given to us or we write it on our formula sheet. But I'm pretty sure that's what it is. Where the value of ESI is. Bop. So this is the first important equation that we're going to want. We can confirm that over here. So first things first, he might have a question where he asks you to like pick the difference between bias conditions or just band conditions. So there's a PowerPoint where where he has the energy band splits up. Yeah, he redoes that and then he talks about all the energy bands. So there's one slide where he has all of This seems important. All right. So there's a couple things here. Oh, this is for onset of inversion. I'm not sure if we need that right now. Yeah, so this is a slide I was looking for. So this right here is a really good slide because it, you know, takes all the information that we need for band stuff and brings it into one spot. And also, look, it gives you all those conditions that I was talking about earlier. So I was right in saying VG equals 0 is flat band. Did I say this was depletion? No, this is what we answered since it was asking for depletion. This is what I did. I actually was right about this. I don't think I made a comment about this one. I don't think I directly said it was inversion. I'm happy I got 3 out of 4. It's good enough for me. But this slide right here, I'm not sure what the upper limits are for the information we're allowed to have on our formula sheet. But if anything, I would say right there, this line of information right here, these conditions, if you were to write VG less than 0 is equal to accumulation, VG equals 0 flat, like those conditions, if you were to write those conditions down, I'm sure that's like well within the rules to have that information available to you. So I would definitely keep that, write that down, because that's definitely going to be important, whether it be for solving multiple choice questions or assisting you later on if it arises that we need to draw or be able to pick between band conditions. So I'm going to write these down. Everyone ready for Thanksgiving?
Yes.
Yeah, I'm ready for Thanksgiving. I've had about enough of this.
Oh yeah.
All right, so there's that information. That's good information there. And here's the other information I was looking for. This is, again, more information that might be useful to stick on there. It's important to note there that there isn't a condition for flat band here. I'm pretty sure the reason there isn't a condition for flat band is because at flat band it equals 0. I'm pretty sure. So that's probably more information that's probably useful to have down. I just realized a better format to write this information. I'm going to restart. I'm going to rip this out. We're actually pushing up on the limit on the timer I was putting on this. So as I said, I'm going to send the formula sheet to the GroupMe and then ask, you know, the hive mind of the GroupMe to add formulas if needed. So since we're pushing towards the time barrier that I put for this one, I'll end it here and then send it into the GroupMe and send my formula sheet into the GroupMe in the next hour or so, along with the link to the video recording. So we can everyone can get to the same information at the same time. And this is in the pursuit of not making a video that drones on for 2 hours long because I spent an hour looking for formulas. I'm going to spare people that. And it'll also make it so the YouTube upload goes a bit quicker. So I'm going to stop the screen share for this then. All right.